Hello. So in this tutorial series, we are going to see how we can analyze astrophysics data with Python. For this first tutorial, we are going to basically see how we can open a set of files. In this case, will be fit files. So we are going to see how to open a set of fit files and then extract some required data we need for our analysis. So I'll take you here to my screen. So here we are. The IDE I'm using is Spider because that's the one I'm used to working with. Use the one that suits you best, the one you prefer, be it Jupyter or PyCharm. It's all to your preference. So let's open the file. So here we are. WASP 127 NERPS 1Z, that's the file that contains the observations made by WASP, made by NERPS actually, which is a spectrograph instrument. As you can see here are the observations that were made for a given night, during a given night actually. So we have a good number of them. So the first thing we're gonna do is to import the modules we are required to work with, the modules we'll need for in order to open this set of files. So from astropy.io, we are going to import fits because we are dealing with fits files. So basically import fits. And the next one, we are going to import the globe module. You are going to see in a few seconds why we need that. It basically helps us to just go through all the files. You are going to see that. So we are going to define a variable. In this case, you are just going to say files, which refers to all the files that are contained in the folder. So we are going to say files equals globe.globe, and here we enter the file path. So basically we'll just enter the file path, which leads us to extract all the data content in all of those files, because as you saw, we have a good number of them. So in order to get the file path, we can just come here and if we click here, as you can see, we have the path to all of these files. So we are just going to copy that. And we can replace that here in the file path. So globe.globe of this file path, that this is the path to all of those files. For this to work, actually, we would have to do a few modifications. We have to change these slashes to the other way around, else Python isn't going to notice that. And we are going to put a star.fits, as you can see here, in order to tell Python, okay, you will go in this file path and you collect, you go through all the files that end with the fits extension and you collect the data. And for that to work, we need to reverse this slash the other way in order to have the correct file path in Python. So we do that. Okay, here we are. But we need to add one last thing actually in this correct file path in order to make sure that it goes individually to each of these files, and get the data. So we need to add one last thing, as I said, and that's kind of a boolean, a recursive equals true. So basically what we are telling Python is, okay, you go through the first one, it ends in fits, good, you go through the second one, and so on. And what it's gonna do is it goes through individually through each of these ones. After the first one, it goes to the second one, the third one, and so on. That's the need for adding the recursive true. So in order to illustrate what it does, we can just enter a print. We just say files 0, which means like the first of these files. We just basically tell it Python to print, to give us the first element of these files, and we run that. And as you can see here, it gives us the complete path to the first of all of those files. And you can check, it corresponds to this one right here. Yeah, it's exactly the path to this first file. We can change this and enter another one. And in this case, it gives us the path to the 10th, to the 11th file, because it starts counting from 0. You can see the path here. It corresponds to the 10th file. You can just change and you tell it, give us the 52nd file, and you get it. It basically gives us the complete path to the 52nd file, which should be the last one in this case because we have 52 in total. Trust me, I counted all of them. Okay. So now we define a header unit. Actually, it's just a variable, actually. Just call it HDU. You can call it whatever you like. It doesn't really matter. So we are going to like open the file. So it's just like a variable, and we assign to that variable a fits.open files, and we index it with the file we want to open, basically. So saying file 0, it will open the file, the first file index 1, and if we run that, basically what it has done is it has opened file 0, the first file. So we can define here another variable, and we can call that data, and we tell Python, okay, give us HDU 0, so the first element of HDU, and we use here a special function called the header function. So basically, the header function is used to like extract the essential data content in this case, HDU, in the first element of HDU. And if we ask Python to print the data we want that, you can see the header function has enabled us to extract all the data content in like the first folder of HDU. And here we have all of the data you can see here. We have everything. We have the temperature set point of the observation. We have the exposure time in seconds. We will have everything here. Yeah, all the data like CHDU0 as giving us all the data for like a first part of the data, if you like, and the header function simply enables us to access that. So if we enter 0:100 inside the header function and we run that, what it does is that out of all those data, it gives us the first 100 elements. And actually it has kind of cut all of that and just gives us the first 100 elements. You can see here we have the observation time, the exposure time, and everything. WASP 127, which is the planet. We have the observation ambient relative humidity. We have the units. We really have everything. Basically, working with the first 100 is enough for what we need to do, because as you can see, there are hundreds and hundreds of data. We can just work with the first 100, and that will be enough for it will contain all the information we need for this analysis, actually, for this first part and for the rest of the tutorial, what we have to do. So we can define another variable. Just gonna call it data2, and in this case we say header unit 1 dot header. So again, it will go and extract all the information contained like in the second path of this header unit, if you like. If you see the header unit as, see these files as containing information in like kind of bulk information in like sections. So HDU0 gives us the first section, and HDU1 gives us like information in the second section. So the header helps us to access that, and basically we just tell Python print data2, just as we print the first, we printed the first one. So we can just mask the first print, and in this case, when we run that, you can see what we have. We have another type of information which is different from the first one, like information in another section. You can see, for example, here we have the wavelength, we have the flux, we have the wavelength error, we have the error on the flux, and so on and so forth. Actually, it contains a bit less information compared to the first one. Yeah, we can just modify that. Yeah, so basically this is what we have, and notice that the data is arranged differently from what we had in the first section, and you're going to see why this difference matters as we move on, because the way we extract the data actually will vary. So here, if we want to get, we are going to try and get the information contained in the wavelength of phi 0. So we are just going to say wavelength equals, and we'll try to extract the data corresponding to this wavelength. Note in this case that wavelength is like inside this column, which means we can access directly the information or the value of the wavelength inside phi 0, which is in this case is the observation we are dealing with, by just literally copying the HDU1.header and just putting in like the value, like, yeah, the value, if you like, what is inside that column. And by so doing, it should enable us to get the value of the wavelength. We can just hide the previous print so that we just have the wavelength, and we can tell Python print us wavelength. So wavelength equals to that, and print us what is inside that column, as we can see it here inside HDU1. And if we run this, yeah, it tells us keyword wavelength not found. Yeah. Let's check why it doesn't work. Yeah, okay. Yeah, so actually the problem comes inside this header. Okay. Remember, the header function is used to access information contained in information content. So actually what we need to put here actually is the data contained inside wavelengths, and not the header contains in the header function. Is not just the appropriate thing to look here, because wavelength is not it's not a key wavelength, it's not a keyword. And when we run this now, you can see what we get here. We have basically the wavelength as an array. Yeah, so actually wavelength was not the keyword. In this case, it's just it contains a value that is hidden inside this wavelength, as you can see. And to access that data, we just need to say data and wavelength, and Python should be able to access that. So it usually happens. Let's try to print another one. In this case, the flux. We basically just copy this and we print here. And yeah, we replace wavelength with flux. Again, we just replace it with the name that is assigned inside that section of the folder, as you can see. And here we can just ask, okay, Python print us flux. And similarly to the previous one, we run this. Yeah, you see it gives us the flux values, the values associated with the flux. So actually all of these names that you can see here, they are not keywords. Yeah, they are just quantities that enable us to go and extract data. So we need to index them. We need to assign the prefix data each time we want to look for these ones. We can try to extract another one, the quality in this case. And basically we just do the same thing. We copy this and we paste here, and we just replace the value flux. Make sure you really have to insert exactly as it is written inside those files, else, as you saw, it won't give us the value. So here we replace it with quality exactly as it's written there, and can print that. Yeah, so here we have the quality. Let's visualize this. Let's run this, and yeah, you can see we have an array containing the quality, actually, which is this quantity here, C type 5, or the label for field 5. Actually, that's how I should be calling them. I should be calling them label. That's the right word. So they're actually labels. So make sure you really have to copy this label as it is. So again, we really need to make sure that we index it, we use the appropriate code or syntax, if you like, to extract data we are dealing with. So now we need to go inside the first section and see if we can extract some data among the first 100 that we had. Remember, we cut it into, and we just require the first 100. So we'll try to extract some of them. And in this first section, you can see there are keywords, contrary to the second section that from which we just extracted wavelength, flux, and quality. Here there are keywords, and those keywords are what you can see on the left column here. There you can see here, isotpld. You can see there's so many of them, so those are keywords and they have a value. It's not like it's different from the second section in which the values were kind of like hidden. So we can just hide the previous print, and we can just run this. Yeah, of course, these are the first 100 values. I just reprinted them so that we can visualize them better. That's the file path, and here are the keywords. You can see on the left column we have all the keywords and they contain a data. So the way we access this data is pretty different from the way we access the data contained in the other section. So say for example we need, let's just select one of them. Here we have exposure time, we have the object. So let's say we want to access this data, the instrument used. In this case, it's NURBS, yeah, which stands for Near Infrared Planet Searcher. Actually, it's the spectrograph that enabled us to obtain this, that made these observations. So I'll just say instrument used. I just write that, and in order to get the information, which is NURBS contained in the instrument used, I need to copy this and paste it here, kind of. But now we don't want to access the data contained in instrument use. So we need to do a slight modification. We want to actually make sure we use the header, actually. And here we enter the keyword, because in this case, we have a keyword, and that keyword, we need to make sure we go and get it inside the file, exactly as it is written. And you can see here the keyword, it's like instrument, capitals, in capitals. So we copy that, and we are going to replace it here on the keywords, because it's a keyword, different from the information contained in the other section, which was not a keyword. So we have this, and we can print this out to see what we have. Here we go. So we have that, and basically we expect that it should return us NURBS as outcome, because NURBS is the name of the instrument. Let's run this, and if we run that, what do we have? NURBS, yeah, cool. So it returns us the name of the instrument, NURBS, Near Infrared Planet Searcher, which is the name of the instrument, actually. So NURBS. Okay, let's look for another one. Let's see, we want to get, yeah, okay, that was, okay, maybe the exposure time, yeah. Let's say I want to get the information contains under this keyword, the keyword associated to exposure time. So we just define a variable called exposure time, and basically just as the previous case, we copy this and we paste it here. In this case, we represent instrument with the associated keyword for exposure time, which is X time in capital. So we just copy that and make sure we insert it just as it is. So we do this. And we can print the value, just say print us, copy that, and I paste here, exposure time. Yeah. So print exposure time, and basically we expect to have the value that is just there on the right. So we run this, and yeah, you can see it gives us 401.2776, which corresponds to what we have here in seconds. The unit is what is indicated in kind of those square braces there. Okay, we can get another one. Let's see. We have observation start. We have, okay, let's just see this one right here, which is kind of awkward name. Well, so let's see if we can get that. So I will just say awkward equals, yeah, I just call it awkward because it has a kind of awkward name there with values and letters. So in this case, I will just copy the associated keyword to this kind of awkward name, which is LST. Well, I paste it here, yeah, and just as above, let's print awkward. Yeah, kind of cool name. So print, I paste it here, awkward. Okay. So we expect that it should return us this data. We run this, and yeah, that's what we have. 24,018.924 in seconds. And yeah, remember that this is for phase 0. I can, if we want, we can change the file number. In this case, let's just say 11. Remember, we have 52 files in total. I counted them, do not worry, trust me for this one. So if we run this for file 11, which is actually the 12th file, excuse me, we have here the data for the 12th file, and you can see it has changed. NIPS doesn't change, it remains the instrument used, but the others change actually because the observations have changed. So we have all this set of data for the 12th file. So that was it. Basically, this is how we can open and access the data content with these files. Thanks, and I see you in the next tutorial for the next part.